Okay, so we have learned about Gibbs free energy, we have learned about cell potentials, and we have learned about equilibrium constants. These three quantities are related to each other. So here's a triangle of them, and by the end of this chapter, we will have equations relating all of them to each other. For a spontaneous redox reaction, delta G is going to be negative. And remember, Gibbs free energy, that's the most accurate way to predict is this spontaneous or not. Increase in entropy suggests that it would be spontaneous, but there are ones with negative changes in entropy that are spontaneous. But delta G, if it's negative, spontaneous reaction. If the standard cell potential is positive, it's going to be a spontaneous reaction. If the equilibrium constant is greater than 1, it's going to be a spontaneous reaction. Because an equilibrium constant greater than 1, and you're starting with just reactants, in order to get to equilibrium, it has to go forward, right? It has to go forward a fair amount. So non-spontaneous are the opposite. Delta G is positive, E cell is negative, and K is less than 1. It bothers me that delta G and E cell don't have the same sign for this. And it also bothered me that delta G and delta S didn't share the similar sign convention. So the way I think about it is the standard cell potential and change in entropy, they have their own sign convention. Delta G, delta H, those guys are what seem like regular to me. So E is just odd. Any questions? So the potential difference is potential energy difference per unit charge. And that corresponds to the maximum amount of work per unit charge. So potential difference in joules divided by charge in coulombs. And we can write this as W max, the maximum possible amount of work. And the charge we can write as Q. So then E is W max over Q. Well, we learned that the maximum work done by a system is related to, oh wait, never mind. Jumping ahead of myself. We're just rearranging this right now. So if we multiply both sides by Q, and yesterday I didn't know where the minus sign came from, and today I don't know either. The sign on work depends on who are you talking about. You talking about the system? You talking about the surroundings? So this is talking about the maximum work done by the system. The system doing work is going to be negative. The system having work done on it is going to be positive. And so I think that's where it came from. But the maximum work is going to be negative, the charge times the standard cell potential. Come on. So the charge, it's measured in coulombs, and we quantify using Faraday's constant, capital F. It's the charge in coulomb of 1 mole of electrons. So that's how it relates into chemistry. It's a mole of electrons. Whatever the charge in coulombs on 1 mole of electrons, that's what F is. And that happens to be 96,485. I don't expect anybody to remember that number. I have a hard time myself, even to the next slide. I often get the 8 and the 4 backwards. But it's a constant. It's on the table of useful information. So it's this much charge for each mole of electrons. So then the total charge in this chemical reaction is the number of moles of electrons times this charge per mole. Okay? So W max is equal to negative Q standard cell potential, which equals, now we're substituting in NF for Q, negative NF times the standard cell potential. Standard free energy is the maximum amount of work that can be done by the reaction. So that's W. So we can put delta G in here for the W, and we get delta G equals minus NF E cell. N's the number of electrons, number of moles of electrons in the balanced chemical equation. F is Faraday's constant. This is the standard cell potential, and that'll give you the free energy. So if the standard cell potential is positive, is the reaction going to be spontaneous? Yes. If the cell potential is positive, it's spontaneous. If the standard cell potential is positive, that means that delta G is negative. And so I believe that's why there's the negative sign in there. Okay, use tabulated electrode potentials to calculate delta G for the reaction. Is the reaction spontaneous? So this will also review some things we talked about on Tuesday. So it's not absolutely necessary to take this equation apart into half reactions, but especially until you get familiar with it, I think it's a good idea. So we got 2 sodiums. Yeah, the highlighter's not a good thing to write with. 2 sodiums. And the other reactant is 2H2O. So one of these is going to be a reduction, one's going to be an oxidation. So I'm going to look at the products to see, well, what goes with sodium? Well, the sodium ion, right? So 2 sodium ions, aqueous. And then there's got to be electrons involved. Identify the side that's more positive. This has a positive 2 charge. This is 0. The electrons are going to be in there so that the charge is equal. So we must need 2 electrons on this side. That thing is losing electrons. That's the oxidation. We've got H2O, and then we're going to put the rest of these guys in here. I'm going to leave a space because I know it's coming. So we've got hydrogen and 2 hydroxide. That's also going to need electrons. If you did this one correct, it's going to be this same number, and it's going to be on the other side. And if we check that, here we have negative 2. This side is more positive at 0, so that's where the electrons need to be, 2 electrons. So this is like taking that balancing redox reactions and going backwards a little bit, okay? So this is the part where you've got both half reactions balanced, equal numbers of electrons, and the next thing is you add them together. So we took what was added together, we separated it, because we need to see what the 2 half reactions are. So this one has sodium on one side and sodium plus on the other side. And so let's find that in here. So the standard cell potential for that is negative 2.71. So I'm going to write that in here. And the other one is H2O on one side, H2 and 2O minus on the other side. And that one's negative 0.83. The Book's method is identify which one is the cathode and which is the anode, and take the cathode and subtract the anode. I don't like that. I'm going to look at these and say, which one is written backwards of how it is in the table? The sodium, right? So this has sodium ion on the left, and this has sodium ion on the right. The equation is written backwards. So I'm going to change the sign on the the electrode potential. Okay? Do not multiply by 2. That's going to come in, but it's going to come in later. So then we just need to add these together. And I'm getting 1.88 volts. That's the standard cell potential. Any questions about that part? So, in case we forgot, this is the equation we're going to use. Delta G equals negative NF E cell. So we calculated E cell. We need F. F is 96,000, I think it's 485 coulombs per mole of electrons. I did it right. And then we need N. N is the moles of electrons in the balanced chemical equation. That's where this 2 comes in. This one is losing 2 electrons, this one is gaining 2 electrons. So N equals 2. Any questions? We're not looking at the number of electrons over here. We're not thinking about, oh, well, this one got multiplied by 2. We're just going to look at what was it in this balanced equation. We're taking apart a balanced equation, and so the numbers of electrons are going to match, and that's the number we need to use. Any questions? So now we can put, I think I paused it by accident, so I'm just going to let it sit here for a few seconds so anybody watching can at least pause and see what we did. Okay, consider this non-spontaneous reaction. You got iodine and bromide, and that could go to hydrogen plus iodide plus bromine. What's weird about that? Is that balanced? No, there's hydrogen on one side. And I'm looking at that and I'm thinking, well, why didn't I see it yesterday or the previous semesters that I used this slide? I think that's a mistake. Okay, so got distracted by that. This is non-spontaneous. So iodine would be reduced here, and bromide would be oxidized, going from -1 to 0. Iodine's going from 0 to -1. But iodine does not oxidize bromide, and so we have 3 choices. Bromine's more electronegative than iodine, so we don't expect bromide to give up an electron to I2. Or the opposite, I is more electronegative than Br, therefore we don't expect I2 to give up an electron to Br. Or Br minus is in solution and I2 is a solid. Solids do not gain electrons from substances in solution. let's talk about C. Is that true? No. If that was true, none of these cells that we were making could happen because they all have a solid electrode in them, right? So that's just ridiculous. It's not that one. So here, we actually don't need to understand the reasoning because they're exactly opposite. And this is saying bromine's more electronegative than I, and this is saying I is more electronegative than bromine. And in Chem 1A, we learned how to figure that out from the periodic table. And so bromine is closer to fluorine. Fluorine is the most electronegative element. So if you're looking in a column, whichever one's closer to fluorine is going to be more electronegative. So this statement, iodine is more electronegative than bromine, is not true. I'm sorry. Yes, yeah. Don't mind me. My brain's all over the place. Yes, this is the correct one. So bromide is more electronegative. It has a bigger attraction for the electrons. And so here, bromide has the electron, and it's strongly attracted to it, more strongly attracted to it than iodine is. And so it's not going to give up its electron. So A is the answer. Any questions about that? That's not a good exam question. It's good to talk about, but that's not a good exam question. Okay, let's look at this relationship between standard cell potential and the equilibrium constant. We learned that delta G is equal to negative RT natural log of K. And we just learned that delta G is also equal to negative NFE cell. So if these things are both equal to delta G, then they must be equal to each other. And so here we just took this one and said, well, it's equal to that one. And now we're going to do a little rearranging. We're talking about standard conditions here. So the temperature should be 298.15. That's standard 25 degrees Celsius. R is the ideal gas constant. F is Faraday's constant. And so we can plug those things in. Divided by N. I'm sure there's a historical reason for this, but electrochemists prefer to use base 10 logarithms. So you can convert natural log to base 10 log. The natural log of K is equal to 2.303 times the base 10 log of K. So we go in there. And we say, okay, well, that's 2.303 log of K. I'm not going to make you derive that. It's okay if you didn't understand how that happens. But I think it's good to show you that, we're not just making this stuff up. So this is the equation that relates standard cell potential to the equilibrium constant. Any questions? Use the tabulated electrode potentials to calculate K for the oxidation of iron by hydrogen. So let's write down that equation before we forget it. Standard cell potential equals 0.0592 volts over N times the base 10 log of K. So we're trying to find K. What do we need? This is what we're going to solve for. The other variables are n and standard cell potential. So here's our balanced equation. We need to pull it apart, see what the two half reactions are, so we can find the standard cell potential, and also identify how many electrons are being transferred. So 2 iron, that's going to match up with 2 Fe3+, and that would need to have 6 electrons for it to be balanced. 6 hydrogen ions are going to gain 6 electrons and become 3 hydrogen molecules. So these are the equations we're looking for in the table. One of them is here at the very top, and the other is right under it. You need to be a little bit careful because this is Fe3+ and Fe0. We don't want to get that mixed up with Fe2+ and Fe0, or there's another one in here where Fe3+ goes to 2+. Yeah, be careful of those. So the top one, the table tells us 0.036 volts. And for the bottom one, it's exactly 0 volts, because that's what we defined as 0. Then we see one of these has to be backwards. You can identify it by looking at the Fe3+, or you could look at the electrons. This one has electrons on the left. This one has electrons on the right. It's the opposite, so change the sign. Any questions? Otherwise, you're looking at this, you're saying, okay, this is oxidation is loss of electrons, so this is the oxidation, and oxidation occurs at the anode. I need to have the cathode minus the anode. So this must be the cathode, so I'm going to take this, and I'm going to subtract the negative 0.036 and get the same answer. But that just seems like a lot of thinking about stuff where you could easily get something backwards, right, and end up with the wrong answer. So I don't want to do that. So that's our E cell. What's N? 6. Because this one's losing 6, this one's gaining 6. So E cell, 0.036 volts, is equal to 0.0592 over N times the log of K. If you don't like algebra, you can use the solver to solve this. I'm going to combine all the numbers. That's 0.036 multiplied by the bottom and divided by the top. $6,486. And then to get rid of the log, we're going to raise 10 to this each side. So 10 to the power log x, log q. Okay. It's not a q. It's not an x. It's the letter K. It's one of my initials. I should know that one. Mrs. K. Okay. So we raise 10 to this power. We raise 10 to that power. And so on the left side, that makes the logs disappear, and we just get K. It is okay. It's fine. There's more numbers, but What are the units on K? It's unitless. How many sig figs should this have? This only has 2, so we're going to round that to 2. So that would be 4,500 or 4.5 times 10 to the 3. Any questions? So here we have all of the relationships. We learned this in chapter 19, and these are the 2 that we learned today. So, that might be a nice thing to have as a screenshot on your phone or something to refer to. I really don't like these. Redox reaction is an equilibrium constant of K equals 1.2 times 10 to the 3rd. Which statement is true regarding delta G and E? Well, it would be really helpful to be able to look at those equations. So here, K is a big number, 1,200. So here we have K and some constants. The natural log of a big number is a positive number, right? And if you're not sure, just take the natural log of that number and you'll find out, oh yeah, that's a positive number with a negative in front of it. So then delta G is going to be 0. I also seriously question why it says G cell. Pretty sure that shouldn't be in there. This is what happens when you copy and paste and forget to go back and erase things. So from this guy, we can figure out that delta G0 is less than 0, sorry. It's negative. So delta G being positive, that doesn't work. So those are both off the table. And then we can look at this one to get the sign of E. So this is base 10 log of a big number. Again, that's going to be a positive number. The log of like 0.5 or 0.1 is going to be a negative number, but if it's greater than 1, it's going to be a positive number. So this is a positive number multiplied by a positive number divided by a positive number. So that tells us that E cell is greater than 0. So E cell must be positive and delta G must be negative. Any questions? Would this be spontaneous? Yeah. It's got a big K, it's got a negative delta G, and a positive E.